Alright, in this video what I'm going to cover is a sort of a review for the second exam where we're going to talk about z-scores and hypothesis testing. This is really for chapter 7 and 8 in the Nolan and Heinzen book, and it's going to cover z-score testing with hypothesis testing steps, power, effect size, and confidence intervals. Alright, so this is just more examples of how to work null hypothesis testing. So the first example, a company wants to know if they raise your price, are we going to lower satisfaction? Because increased prices often will lower how happy people are. So they give people the satisfaction survey with a new customer to see if the customers would drop the service with a price increase. So if the satisfaction survey scores are low, that's bad. So at the normal price, satisfaction's 4 points with a standard deviation of 1.2. So these are the two important parts. So that's going to be mu and sigma. After the price increase, they've given you these scores using p less than 0.05. Is that a significant drop in satisfaction? So you got to think about the scores going down is what you expect because people are going to be unhappy with the fact that you've raised the prices. But we're going to see if it's a significant drop in price. I'm sorry, a significant drop in satisfaction, which would be bad for you. Okay. All right. So, step 1 is our assumptions. Okay. So, is the DV scale? Yeah, it's an interval. Okay, so it's an interval, at least an interval. They didn't tell us a whole lot about it, but most satisfaction surveys are interval type scales. Right? And then the second question would be random selection, right? If I have a list of all of my customers, I could. So I could randomly select specific customers to give the new price to, but I don't think they really did in this example. What they did is they gave all the new customers the new price. So I could randomly select, but in this particular example, I didn't. Last one is the data normal. And that's going to be no, we can't assume it's normal because n is less than 30. Okay, so remember the assumption is it normal? And often we can assume normality for the sampling distribution if n is greater than 30. Okay, so we met one assumption, the most important one. The other two, not so much. All right, so for this second step in hypothesis testing, let's list out who our sample is and who our population is. Okay, this is really still part of step 1, but it's kind of 1 and 2 together here. So the sample is the people who got the new price. And the population is the people who are on the old price. So if I want to come up with a research hypothesis and a null hypothesis for that, let me repeat these here. What am I expecting to have happen? Well, it always helps if you label the DV too. The DV is the rating. So we've got the rating if I have the new price and the rating if I have the old price. And so I'm expecting people to rate the scores lower if they got the new price, higher than or equal to if they got the old price. So this is a one-tailed test, and it's a less than test. Or we're expecting the scores to go down. Okay. So for step 3, oops. Okay, I'm apparently missing some slides here. So what we'll do is erase this one. So everybody got this thing. Back it up if we need this step again. Don't have enough space. Erase all this. Okay, so that's step 2. Now, in step 3, what I did was calculate the mean for the sample. So we've still got our sample here and our population here. Okay. So for the new price, the average score was 3. So I used SPSS to calculate descriptives. There's a separate video for that if you're interested. And the number of people was 10. From the problem, I got that the mean score for the population is 4.0. So the sigma was 1.2, so that makes standard error 1.2 divided by square root of 10, so n comes in over here, and I got 0.38. So the population standard deviation or standard error is 0.38. So in step 4, so this is 3, here's 4, we're going to figure out the cutoff score. Since this is a less than test, we're going to make it negative, and it was 0.05 from the problem. If you back up a couple slides, here's 0.05. Okay. So that makes it 1.64, because remember z-scores are always the same. So we're seeing if the scores are more negative down here, 1.64. This would be fail over here. This would be reject over here. Okay. And then step 5 is let's actually calculate the z-score. So we've got the mean sample score, 3, minus mu over here, which is 4. So 3 minus 4 divided by standard error, so 0.38. That's mean minus mu divided by standard error. If you calculate all that out, you get negative 2.63. So we are way over here, our little class over here. And so I would reject the null, because 2.63, negative 2.63 is less than negative 1.64. So it is out here in the rejection region. So if you think about this as our little VW bus that's driving, it has crossed the finish line, and we are rejecting the null. So for effect size here, we're going to calculate D. And it's mean minus mu, still same as Z, but now over sigma. So remember that Z is mean minus mu divided by standard error. And so that's how we got 3 minus 4 divided by 0.38. It's a terrible 3. There we go. So I had negative 2.63. But this one is going to be 3 minus 4 divided by 1.2, which is negative 0.83. Okay, so the D score will always be less than Z because the denominator is always going to be larger. Okay, so Cohen's D is a form of a z-score. It's a z-score with the population numbers instead of the sample numbers. So we've got mean minus mu, that stays the same on the top, but sigma turns into standard error when we're talking about Z. Okay. This is a large effect size. Remember, 0.2 is small, 0.5 is medium, 0.8 is large. Okay. So what does all that mean if I take all this together? Well, they had a significant decrease in satisfaction scores. And a significant decrease in satisfaction scores with a large effect size means that people aren't too happy with the new pricing. Okay, so their scores, their satisfaction scores went down significantly with a large effect size. Okay. So let's see here. Let's do a second example. So we've got 50 dogs. So here's N. We're tested with this new dog training program. They had an average obedience score. So this is the mean, the sample mean, our 50 dogs, 5.6. The old program had an average score of 3.4, so that's mu, and a standard deviation of sigma. Now, if you're having trouble telling which one's which, you should know that when they put standard deviation in the same sentence as the population mean, that's a good cue that this one's mu. So if it has the standard deviation and a mean in the sentence, that's a good sign as for the population. Okay. We're going to use 0.01 as our significance level here. All right, so let me write a little smaller this time since my slides are goofy. So step 1 is the DV scale. So this is assumptions. Okay, so DV is scale. Oop. Right. And this is a dog obedience training program, and they have a score of 5.6 that looks like a decimal. So I would say it's at least interval. It's likely a ratio scale. They don't totally tell me that, but I imagine we're talking about number of tricks performed, number of actions taken, and that would be a ratio scale because 0, they could do nothing right. That would be my dog. So, did we randomly select? Since we have all of the dogs that come through the program, I guess we could, probably not, but we could randomly assign some dogs to do the new program and some dogs to do the old program. So I would say, yeah, we could probably at least randomly assign, if not randomly select, because we do have access to all the dogs in this training program, but probably not all the dogs in the US. Yeah, so we can randomly assign. Is it normal? I would say yes, because we have at least n of 30. So for step 2, we're going to list the sample and the population. So our sample is all the dogs who took the new program versus all the dogs who took the old program. And so our DV is going to be their score on the obedience test. So don't, when you're setting these up, don't do new program versus score, because they have scores for both the new and the old. So you got to think about, what am I comparing, and then what am I comparing them on? So who are the two groups that we're comparing, and then what are we comparing them on? And that's where you get it in the DV. So this little part isn't required, but I have found that it helps people if you write the DV out to the side so that you know that you've got your two groups in your DV and not IV versus DV. Okay. All right. So let's do the research in the null now. Yep. So we've got our new program and our old program. We're looking for a significant increase in their program score, so we're trying to make dogs better faster. So that means for the research hypothesis, we're going to go up, and then this is going to be less than or equal to. So this is a one-tailed test that is greater than. Right? And so let's see all the numbers we need here. So we've got our mean is 5.6 for the sample. We got 50 people. Population mean is 3.4. The standard deviation is 2.5. And then standard error is going to be 2.5 divided by the square root of 50. Right, so it's standard deviation over the square root of n, which is 0.35. Okay. Ah, what happened? Go back to PowerPoint. There we go. Okay, so 0.35 is standard error. So I've set this up again where samples on the left, populations on the right, because that is how the math works to test for Z. So that'll help keep you straight. Okay. So what next? Step 4, we're going to come up with a cutoff score. It's going to be a positive test because it's a one-tailed test. And what we're going to use p less than 0.01, so it's going to be positive 2.33. Because that's what the scores always are. So this, everything out here, so 2.33. This over here will be fail. This will be reject. Okay. And let's see what actually happened in the study. So that's the critical score, the cutoff score, where our little bus is, our VW bus is trying to cross the finish line, because that's all I can draw. Let's see what people actually scored. So we've got Z is equal to, again, mean minus mu divided by standard error. So I've got 5.6 score for the sample minus a score for the population, 3.4 divided by 0.35, and that is 6.29, because your instructor is bad at making up examples. So for step 6, I definitely am going to reject the null, because Z-score of 6 always gets rejected. It's way out here in space. We're way past the finish line. And so that is a large difference between the old test and the new test, where the new program has a higher score. Now, if I wanted to calculate a confidence interval on that to determine, like, well, how much should I believe this 5.6 number? Like, what would happen again? What we're going to do is we're going to do a two-tailed confidence interval, because those are more normal. You can do a one-tailed confidence interval where you would only do the top end, because that is what we were predicting, a higher score, but most people do two-tailed CIs. And so the formula for that is going to be this sample mean. This is the sample, don't fill in the population here, plus m minus a Z critical, or Z cutoff, okay, for p less than 0.01, for a two-tailed test times standard error. So for the lower end, what does that mean? It's going to be 5.6 minus 2.58. So here's where it becomes the lower one, that negative number there. Times standard error is 0.35. For the upper confidence interval, it's still going to be the mean, 5.6, now plus the same thing, 2.58 times 0.35. If you do that all mathed out, it's 4.7 to 6.50. So if the mean is 5.6, it needs to be in the middle here. So it has to be an equal number on each side, and the lower one should be smaller. Okay, it might be more negative, but it should be lower than the sample mean, and the upper one should be higher than the population mean. I'm sorry, sample mean. And so where did I get this number 2.58 from? Well, p less than 0.01 with a two-tailed test is 2.58. Remember, so plus and minus 2.58. I didn't use 2.33 because that's a one-tailed test. All right, let's try number 3. So Netflix is sort of famous for their rating system, and they've put a lot of work into it. And for a while, they were offering people a lot of money to come up with a rating system that would get closer to your score. So how accurately can they predict your rating for a TV show? Because if they can predict your rating pretty accurately, they know what to recommend for you. So normally they're within 1 point of your score, the standard deviation of 1.35. The new system is within 5 points of your score. So anytime you see normal, that means it's going to be the mean, the population mean, population standard deviation. Oopsie, no M yet. Sigma. The new system is within 0.5 points of your score, so that's the sample mean. And we're testing it with 100 people, so that's N. Is there a difference in these scores? We're going to use p less than 0.05. We didn't predict a direction. We really want the scores to go down because we really want the scores to go down because that means they were getting closer and closer to your score. But we didn't predict a direction. Maybe the scores are getting further away, and that would be bad. All right, so for step 1 is the DV scale. Okay. Yes, it's probably interval. Actually, it's going to be a ratio scale because they're talking about how far away are they from your score. So they could be perfectly on your score and like hit it just right. They guessed your score perfect every single time. I mean, that's probably not going to happen, but they could. So it's actually going to be a ratio scale because they're getting how close are they to your score. So random selection. We don't know how they picked these 100 people, but they most certainly could because they have a database of all of their customers. And then is it normal? Yes, because we've got way more than 30 people. We've got 100. Okay. So let's, for step 2, label the sample and the population. Okay, and then the DV, just help ourselves out here. So the sample is this new system. So you see a trend here. New versus old. People trying to update things. And then let's talk about what's the other one here. So let's do the old system. And then what's our DV? So how close are they to your score? So let's call that score accuracy or something. So how accurate are they predicting your score? I don't know, we used different here in the example, so what's the difference between the scores? So we're not predicting any one direction, so I'm going to use a two-tailed test, which means it'll be greater than or less than. I'm not picking a side. So that is a two-tailed test there. For step 3, let's label everything we have. So we have the population mean, I'm sorry, the sample mean is 0.5. And the slides are possessed. There we go, 0.5. Sorry, joys of being left-handed with these things. The sample size is 100. The population mean, they're normally within 1 point of your score. The standard deviation was 1.35. And the standard error, so I'm going to take 1.35 divided by the square root of 100, so divided by 10, equals 0.14 if we round up. So we've got a standard error of 0.14, standard deviation of 1.35. So let's move on to step 4. We're using p less than 0.05 and a two-tailed test. So that means it's going to be plus and minus 1.96. So we're going to do both sides. Okay, so our little car can go either way. So this is fail in here, and this is reject out here on both sides. Okay. And then let's see here. Let's calculate the actual score now. So z is equal to the mean minus mu divided by standard error. So I've got 0.5 minus 1 divided by 0.14, and that's negative 3.57. So the scores are going down, but remember that's not always a bad thing. This is what they want. We are getting closer to your actual score. A score of 0 would be perfect in this particular example. So we're way out here at negative 3.57. This was 1.96 on both of these. So we are going to reject the null. So this is step 5, this is step 6, because the score is much lower than expected. Okay. So we're saying that the scores are going down. Now, let's try an example for power. So power is one of the most difficult topics, especially in this section, but overall power is just kind of hard. And I'd like to give an example of how can I calculate the power for this study. So I rejected the null, but like how much power did it actually have to find that difference because I said it existed. Okay, so the first thing you do for power is you write down everything you have. So I have my sample mean is 0.5. My sample size is 100. My population mean is 1. My standard error is 1.35. I'm sorry, standard deviation is 1.35. Standard error is 0.14. The second thing you do is you calculate what mean would I have needed to reject the null. Now this is where you have to make a decision. You can do a two-tailed test for power, but it's just ridiculously stupid. So I would tell you to pick a direction. So we're going to go p less than 0.05. And I know I want the scores to go down because that's the direction that would make the most sense. That means that we are getting better at predicting your score because we're getting closer and closer to the score. So there's a less of a difference between your score and what I would have predicted your score to be. Okay. And because I want to go with a less than test, that makes z negative 1.64. Okay. And so what I'm going to do to calculate my mean needed is that I'm going to take z critical times standard error plus the population mean. That's the tricky part right here. Oops, I didn't have to write that out. Let's try that again. Boop, boop. Okay. Because what we're doing is we're finding what mean I would have needed to reject the null. And so you don't want to fill in the sample mean because that's the mean you actually had. So start with what would I need to get. So let me fill all that in. So I got negative 1.64 for less than test times 0.14 plus 1. If you do all that out, it's 1. Oops, it's not 1 anything. Try again. 0.77. So to reject the null, I needed at least a 0.77. I had a 0.5. That's why we rejected the null. Okay. So this is the mean needed. And so how much better am I doing? Okay. And so the answer might be not enough, but in this case it is. So what you're going to do is calculate the z-score difference between the sample mean you have and the mean you needed. Okay, so that formula is mean needed minus mean have, okay, or the sample mean divided by standard error. So I have 1 or 2 slides for this. No, only one slide. 0.77 minus 0.5 divided by 0.14. So that means my z is 1.93. And so I have a z-score difference between what I have and what I needed of 1.93. All right, if you've got that, I'm going to erase some of this so I have some space to write up here. So what's the last step? Well, we need to figure out what my power is. So I'm going to mark 1.93 on my graph. We've got 0 here in the middle. And we went with a less than test. I know that was the part I just erased, but I promised you we went with a less than test. So everything this way is power because it's less than. If you fill that in from a z-score chart, what we've got is 2.68 out here, 47.32 here from z to 0, and then 50% from 0 to infinity. So if I add those two together, I have 97.32% power. So what does that mean? It means that I had a 97% chance of rejecting the null if I should have. Now, I mean, that's saying that you're rejecting the null when the null is false. And so when I calculated with my hypothesis testing steps, I was pretty sure the null was false because I rejected it. But I had a 97% chance of finding it if it is actually false. Okay, last example. So we've got 10 students, that's N. We're tested with this new language program, so we got all the numbers, so we're going to have to calculate, there we go, calculate M, the sample mean. The normal score is 85%, that's the population mean, and the standard deviation is 14%, and we're going to use 0.01. Now these are percentages, don't let that confuse you. I know z-scores are in percentages, but just leave them as percents because we're talking about average scores on an exam or something. Alright, so for step 1 is the DV scale. And since it's a percent, I would say yes, because percentages are ratio scales. Oops, no, ratio scales. All right. Did we have random selection? And probably not, because these are people. We don't really have access to everybody, but we could randomly assign people to take the new one. So I would say, yeah, I could randomly assign you to the new language program versus the old one. All right, is it normal? And I would say, I don't know, so I can't assume so because N is less than 30. So for step 2, let's label our sample and our population. All right, we're going to do research in our null. That's an R. Okay. So we've got our new program versus our old program. Remember, the DV is your percent correct. Okay, and let's see here. Are the scores statistically lower? So I actually did a prediction that their scores would go down with this new language learning program. Okay. So I would say that they're less than, greater, and then greater than or equal to. So this is a one-tail test where it's less than. All right, step 3 here, so this is 2 and 3, is to label your numbers. So my sample mean is a 74. I calculated that by using SPSS and doing descriptives. My sample size is 10. Okay. Population mean is 85. And then my standard deviation is 14.2. You notice I did not change any of this to proportions. I did this all in percentages. Leave it alone. And then my sample standard error, rather, is 14.2 divided by the square root of 10, which is 4.49. So standard error is 4.49. Okay. For step 4, we're doing a less than test. And then we're using p less than 0.01. So that makes it negative 2.33. So this is reject out here. This is going to be fail over here. For step 5, we're actually going to calculate z. Ooh, goodness, that was not legible. Okay, so we're going to take the sample mean minus population mean divided by standard error. So I've got 74 minus 85 divided by 4.49 is negative 2.45. And what I'm going to do in step 6 is reject the null. Okay, so why am I rejecting? Well, negative 2.45 is just barely past our cutoff score of 2.33, but it is still past our cutoff score. Right? So we are going to reject the null because it is further out than the cutoff score. And for good measure, let's do effect size on this. So remember, effect size is mean minus mu divided by standard deviation and not standard error. So I got 74 minus 85 divided by 14.2. So it's still a large effect. It's close to large. It's negative 7.77. So remember that 0.8 is close to large. All right, so that's the end of some examples for chapter 7 and 8. It covers how you do z-score hypothesis testing, confidence intervals, effect size, and power.